All right, we're going to be doing a little bit of bullet math today. In case you don't know who I am, my name is Davin Sunvik with The Catch Today, and we normally talk about hunting and fishing. However, I do want to create a bullet math series, and what we're going to do today is determine whether or not the quick version of calculation or the long version of a calculation is worth it. Now, we're not doing the advanced calculation. We're going to show that one in a different video, but this is the difference between a beginner and intermediate calculation when it comes to changing wind direction. So the wind direction is going to change. So a couple of formulas that we need to know from the start, and then we're going to have some known information right here that we can just get from a bullet calculator. The advanced version of this is to simply take your rifle out to the range, shoot at multiple different distances, and do a regression on those data points. We're not going to do that in this video because there's a lot of statistics involved in that, and that's going to get way more complicated. So maybe if this gets enough traction, then we'll actually do a legit, advanced version on this calculation. But some things that we need to know. So we can find acceleration by taking a known velocity and dividing it by the time. Okay, so that's great news. And then what we can do with this acceleration is we can plug it into this formula, right? So acceleration is a function of force. So if you have that proportion of force, so that you have dt, that's your proportion of force times force, you get acceleration times time, and you get velocity, right? So another way to it's just another way to write this formula up here. Plus your initial velocity, right? So you got to have a starting point in your velocity. So if you have your acceleration times your time plus your initial velocity, you get your current velocity. Now there's a couple of ways to find a current velocity, and that's to find the average amount of velocity, which is the distance that something is moved divided by the time that it took to move it. And then now we have your average velocity, and then you just have to multiply that by 2, and you get your final velocity, right? At the end of the change, or your change in velocity there. So that's going to be important as well. Now we have a position formula, which is going to be super important. Now we have the force. Again, this is supposed to be multiplied by dt. I forgot that little dt in there. But anyway, you take the acceleration, which is just your force times dt, right? So that's your your fraction of your force, divided by 2, times the time squared. And that's the change in time, obviously, right? Plus your initial velocity times time, and then there's supposed to be a plus c here. So you got to add a constant to this. That could be your initial position, but if you didn't have an initial position, if you started at 0, then this formula would work just fine. Now, we got to actually use this a little bit. So we do have a little bit more given information here. So we know that in my 30-06 at 1,000 yards in a 5-mile-an-hour wind, it will push the bullet 43.15 inches. The time it takes the bullet to travel 1,000 yards is 1.77 inches. At 700 yards, we're going to say that the wind goes 5 miles an hour to the left, right? And the left is going to be in positive inches, and the bullet will end up moving 20.62 inches. And the time it takes to do that is 1.05 seconds. Pretty clear, right? All right, then we got to go to that last 300 yards. Well, with a 5-mile-an-hour wind, if the bullet was not moving and then it hit a 300-mile-per-hour wind, it would move exactly 5.74 inches. And the time it would take to do that would be 0.72 seconds. So 72 hundredths of an inch. All right, so if we're all good there, then we're going to move onto the easy calculation, which is just to take the total amount of windage at 1,000 yards and subtract it from our, what we would say is a change in the wind, and just get 37.14 inches. Now, is this accurate? That is what we're going to test using an actual formula. So we get a little bit of calculus in order to get these formulas. I'm not going to go into the calculus here, but we have our initial position. That just simply comes from knowing the wind at 700 yards, right? There's no interruption, so that's going to be a predictable number. We're going to move 20.18 inches to the left. Then we got to add that to our velocity because our bullet is still moving to the left. Just because the wind changes direction doesn't mean the bullet changes direction immediately. So we got to factor that in with this formula right here. Now, we'll find that later. And then we have to add that to the acceleration of that new wind, right? That last 300 yards is going to accelerate the bullet in the right direction, right? So it's going to be moving to the right. And we got to multiply that by the time squared. Now that says 1,000 minus 700, right? So that is the acceleration from 700 yards to 1,000 yards. And this is the time, 1,000 minus 700. That is the time from 1,000 yards to 700 yards, or vice versa. We got the time multiplied by, from 1,000 yards to 700 yards here. So that time is going to exist in two spots in that formula. And this velocity is our final velocity at 700 yards. So let's find that one first. So our final velocity at 700 yards can be calculated by knowing the average velocity multiplying by 2. So the average velocity is going to end up being the position, right, divided by the time. And we get 19.121. So an average of 19.21 feet per second. But at some point it was 0, and at some point it was double that in order to average that number. So what we have to do is we have to take our average, multiply it by 2, and we get 38.43 feet per second. That is how fast, inches per second. That's how fast the velocity of the bullet is moving in the left and right direction. Okay, so bear with me here. There's no gravitational measurement to be had in here. All right, the next one we have to calculate is our acceleration. Well, we're gonna have to get what do you call it? Sorry, I'm making a mistake here. We're gonna have to find the velocity first. So we get the average velocity of 7.9. Then what we do, all right, is we're going to take that velocity and we multiply it by 2 to get our final velocity from that last bit of movement there, and we get 15.94. Well, from 15.94, what we can do is we can divide that by the time that it takes to travel that remaining 300 yards until we get to the target, and then we're going to get our acceleration. All right. So now what we have to do is we have to imagine this curve, right? So the bullet is going to the left for 700 yards, and then it's going to the right, right? But it's not going to go to the right immediately. It's actually going to keep going to the left a little bit further until it starts going back to the right again. So that is what we have to calculate for. That little bit of time where the bullet's not actually moving to the right is going to throw off our calculation on just this simple formula here. So we're going to calculate right now how much it's going to move in that time frame, right? So 700 yards, it's moving to the left. Then for the remaining 300 yards, the wind is moving to the right. Now the wind's moving doesn't mean the bullet's moving that entire time. All right, so we've got our final formula here. So if you want to write this down, you can use this for future reference, right? I'll go ahead and pan on it. So that is the position at 1,000 yards is equal to the position of the first amount of wind plus the velocity of that first amount of wind. That's the final velocity. Then we have our time. This is the remaining time between the first distance of wind and the second distance of wind, plus our acceleration of the second distance of wind times the time of the second distance of wind squared divided by 2. Then we get all of our numbers plugged in here that we calculated up above. All right, so now that we have all these calculated, we end up with 36.35 inches. I wrote it here a little bit cleaner just because I ran out of paper. So now the difference between 36.35 and 37.14 is less than an inch. So is it going to actually make a difference at the range? It could. So just understand that you're going to be off by somewhat. Now, this was in a 5-mile-an-hour wind. In a 10-mile-an-hour wind, these results would be even more exacerbated. So the higher the wind, the higher the proportion you're going to be off in swirling winds when it comes to this calculation. So if this formula helps you, give you a thumbs up. And if you just like the simple version, that's okay too. Comment down below and what you think. And what formula are you going to use?